So let's start. The idea today is to quickly recap what you discussed with Luca, and we go forward towards the introduction of this course. Okay? So this is the idea. You have a user task that usually is an information need. This information need is translated into a query. The query is provided in input to a search engine, which has an input also a collection of documents. And the idea is to answer to this query through relevant documents in order to provide results. Okay? So once you have results, you can possibly refine the query and iterate this circle. Okay, so the main one important question here is how to have an idea of the performance of the system. And so you have already discussed the concept of precision and recall. Just to remind you that precision is the fraction of documents, of retrieval documents that are relevant to the user information needs, while recall is a fraction of relevant documents in the collection that are retrieved. Okay? Good. This gives us an idea of the performance. We'll see later on that there are other metrics. So the main idea is to make the following. You have documents on the columns. You have terms on the rows. And so basically you have a once every time a term appears in a document. That's it. So you get this very big matrix in which you have 0 otherwise. So as an example, Calpurnia is not present in Antony and Cleopatra. Okay? You build such big matrix in order to solve what kind of query. I'm sorry, it's not visible here, but the query that we are considering now as an example is Brutus and Caesar, but not Calpurnia. So we are looking for documents in which there is the term Brutus, there is the term Caesar, but not Calpurnia. Okay, so what can we do? Basically, what we can do, we have Brutus here. This is the vector. We have the vector Caesar. Make an end is extremely simple. We make the complementary for Calpurnia, and that's it. Okay? This is our first solution to the problem. What are the problems with this solution? We're talking about Boolean queries, right? Namely queries that can be formulated as and, or, not, and we will see later on, we will have also other operators on the terms. But what is the problem with this solution? What is the problem? Does it work? It works. But the matrix is huge. Okay? The main problem is that the matrix is huge, not only, but it's also extremely sparse. Sparse means that you have a few ones and a lot of zeros. Okay? So this is the main problem we have. Okay, good. So, in practical, we cannot build such a big matrix. We need a different solution. Okay, so the solution, the standard solution is the inverted index. So what is basically the inverted index? For each term, we build a list of the documents that contain that term. Okay. Each document must be identified by a document ID. What is the purpose of the document ID should be clear a bit later on, but we need something in order to sort the documents. And so doc ID is very convenient. Basically, each time we get a document, we assign a number. Next document, next number, and so on and so forth. Okay? So the doc ID is the identifier for the documents. The main purpose of the doc ID is that you can sort the documents. Okay, can we use fixed array for this? Okay, in principle we could, but what happens when a new document appears that contains a term? And possibly you have all the array already occupied. That's an issue. And furthermore, if you use array, most likely you are wasting some memory, right? Because you don't know in advance the size. I mean, you can estimate the size clearly, but you don't know in advance the size. While I remind you that we started with the consideration that, okay, the matrix works pretty well, but it's huge, so we need to reduce the size. So that's why we use actually lists, and this is an example of an inverted index in which you have the terms, and you have all the documents ID, so the identifier of the documents containing that term. Okay? Does it make sense to everybody? Good. So you have the dictionary. The collection of terms is named dictionary. Each of the document is a posting, okay? And the collection of posting is the postings. Good. So we will see later on in more details that you need to do some kind of pre-processing to the text in order to make it in order to elaborate it in the most effective and efficient way. So as an example, you have a tokenizer. You take a sentence, you take a text, and you split it in tokens. Then you introduce some linguistic modules that, as an example, define a kind of standard normalized form. So you see, those are capital letters. Everything here is small, and so on and so forth, we will see. And finally, once you have those terms, you can index them according to the idea we saw before with the posting list. Good. So we will go, you already saw it, but we will go in greater details to the steps. Tokenization, normalization, stemming. What is stemming? Basically, you are taking the stem of two words. Authorize and the authorization have the same stem. So basically, are, to some extent, the same concept. And then you want to remove stop words, words that actually does not allow you, words that do not allow you, sorry, to get relevant information, right? Okay, good. So this is an example. You have two documents. I didn't act Julius, blah, blah, blah. So let it be with blah, blah, blah. And what you do is the following. First of all, you take all the terms and you assign the document in which they appear. Second, you do the most important operation on this collection. Basically, you order the terms. You sort the terms, sorry. And then you sort also the doc ID. So you sort all the terms according to their, in this example, alphabetic order, and then according to the doc ID. Okay, good. So from here, it's extremely simple. Let's see as an example Brutus. You see, here you have alphabetic order, ambitious, B, Brutus, etc., and then doc ID. Let's take Brutus. It appears both in document 1 and document 2, and thus Brutus has a posting link 1 and 2. And this is the same for all the other terms in the document. We also have something more. What is this 2, 1 here? This is the frequency, the occurrence of the terms in the collection. And we will see that it can be used in order to optimize the query. Okay? Let's forget it for a moment, but later on during this lecture, we will see what is the purpose of this frequency. Okay? Is this clear for everybody? Good. Collection, terms. I'll take all the terms with doc ID. I will sort according to the term, and then according to the doc ID, and then from this sorting, I can finally obtain the postings. Okay? In which, here we have the dictionary, namely all the terms that appear in the document. This is the frequency of that term, and this is the posting list, namely the documents in which that term appear. Good. Okay, this is basically what we already said. So the main question we want to answer, and again, sorry, actually, red and black does not work in this room, so I will change it next time. Anyway, the most relevant questions we want to answer in this course are how do we index efficiently, and how much storage do we need in order to properly manage a collection of documents? Pretty standard questions, okay? Good. Okay. Let's start with the first example of how to process a query. Okay? Namely, how can we deal with the query that the user will give to our search engine? Okay, let's see. The most simple, maybe, query is Brutus and Caesar. So what is the purpose of this query? What is the purpose? I know it's 2 p.m., you had lunch, but let's make it
documents that contain both.
That's it. It's fine. Documents that contain both the terms Brutus and Caesar. Okay? So, we already have the dictionary with the posting list. So, we can get the term Brutus in the dictionary and take the posting list. As an example is this one. Okay? Then we can take the term Caesar and take the posting list. And then clearly we want to merge, we want to intersect, because as he correctly said, we need documents in which both the terms appear. So what can we do with this list? Please, first let's remind me, what is the characteristic of this list? Okay, clearly it contains all the documents in which the terms appear, good, done, but then there is another characteristic, it is sorted, excellent. So why this sorting is useful? I want to merge. Merge means I want to find something that is both here and there. What can I do?
Scan the list.
Is this clear? I mean, I scan. Okay. First I'm here. Is it here? No. Is it here? Yes. So 2, it's okay. 3, is it here? No. 5, stop. 4, 8, yes. So basically, I scan the list simply from the smallest document ID to the bigger. And once I found in both the posting list the same document, I get it because it's part of the answer. That's it. Complexity of this stuff. How many steps do I have to perform? Assuming that X and Y are the sizes of the posting list. X plus Y. Good. Okay? Indeed. I actually do what you said, right? I just walk through the 2 posting lists, and whenever I find 2 postings that are both in the posting list of Brutus and of Caesar, I take it as part of my answer. Okay, and here the crucial point again is that posting are sorted by the document ID. So you see now why sorting is important. Otherwise, you cannot claim that it's linear, right? Okay, good. This is again another picture, but basically I do believe it's clear for everybody. Is it? Good. So this is the algorithm in a pseudo code. And again, what you do is you sort both the lists and then you move with the pointers and if they are, the doc ID is present in both the posting lists, you add it to your solution and you move on. Otherwise, you move on one side or on the other side. That's it. Done. So congratulations, you have answered in a more effective way to your first query, conjunctive query. Okay? Good. Okay. So what kind of query can we answer? Basically, we can answer to what are called Boolean queries, and this is the Boolean retrieval model, in which you can compose and, or, and not. And okay, the idea now is very clear. You see each document as a set of words, and it's, what is interesting in this model, in this Boolean retrieval model, that is very precise. Okay, you can be very precise. It's likely the simplest model that you can conceive to design an information retrieval system. However, has been used in a number of cases. Indeed, is probably the first exploitation of those techniques. And just to give you some example, there are still many search systems that works on this model. Email, library catalog. I didn't know even Spotlight that is this search tool for macOS. Just to give you another example, WestLaw is a pretty big information retrieval system specifically designed for lawyers. You see, tens of terabytes of data and a significant number of users. What is interesting is that the majority of users still use Boolean queries, even if has been proved through experiments that actually different kind of queries. So what are the alternatives to Boolean queries? Do you use Boolean queries in Google? Do you? Do you ever write and or not? No, indeed, you use something that is named phrase queries, okay? Or some kind of phrase queries. So actually, nowadays systems use different techniques because users are more familiar with those techniques. Anyway, in some cases, de facto, users prefer to use Boolean queries, in particular users that had used it for a number of times, for several years. And so with respect to the standard, say, queries that we saw before, it's interesting that you have wildcards. So this is limit whatever here, limitless, limiting whatever. And then you have what is called proximity. This /3 means that within 3 words. Okay, so it means that those two terms must be within 3 words. Okay, this allows you to make more advanced queries, or even you have this /s which is in the same sentence. So you see, even if in its say basic definition, Boolean queries are and or not, you have more advanced systems. So this is another example. What is this? Requirements for disabled people to be able to access a workplace. What is this? This is the information need. Okay? And this information need is translated into a query that in the case of WestLaw is disabled, etc., etc. Okay? Okay, as I told you, many professional searchers still do like Boolean queries a lot, and they use it. But actually, it has been proved that there are other systems that we will see later on that works much better. What is a general problem with Boolean queries? Is summarized in this sentence. So now you remember what is precision and recall, and this is a kind of picture that should clarify it. Okay? But the main problem you have is that the AND operator usually tends to produce high precision but low recall searches. Why? Because you are narrowing the scope, right? You are very precise on what you want. Vice versa, the OR operator gives you, in general, low precision but high recall searches. You are widening. Remember that if you give the whole collection, your recall is excellent, but your precision is very bad. Okay? Because basically you are providing everything that is of interest, but unfortunately also a lot of stuff that is not of interest at all. Okay, good. So this is a general problem with Boolean systems, Boolean queries. And high precision or high recall, it's difficult to, and high precision and low recall, or low precision and high recall, and combine both in order to have a very good, answer to your query is not so easy. Good. Let's make the first exercise, okay? Okay, we want to answer to this query Brutus and not Caesar. Can we answer to this query in linear time? In linear as we saw before, x plus y. I remind you that Brutus and Caesar, we saw it, that means simply walking through both the posting lists, and thus you have x plus y in terms of complexity. Can we do the same with Brutus and not Caesar? And I leave you as an exercise, Brutus or not Caesar. What does it mean? Brutus and not Caesar. What is Brutus and not Caesar? I remind you that Brutus and Caesar are terms, but what we are comparing are the posting lists. So Brutus means something that is in the posting list Brutus and is not in the posting list Caesar. First ingredient. Second ingredient, those posting lists are sorted. So can we do it in linear time as we saw before, x plus y? Yes, we can. Why not? It's basically the same algorithm we saw before, in which you start. Here you have 2, here you have 1. Is 1 in 2? No. 2 is in both, so it's not a solution. We are looking for something that is here and is not there. Okay? So here we have 4, we move to 3. It is not. Because you have the ordering, you can compare it easily, right? So you can move on in x plus y and see and get the correct result. What is another strategy which is less efficient? How can I build the knot? We saw it at the beginning when we saw the matrix. The knot is the complementary, okay? So I should take all the documents, remove all the ones that are in Caesar, and then doing the hand we saw before. Okay, in terms of efficiency, it's clearly not as effective as we saw, as efficient as we saw here. Okay. Good. Okay, so the question is, we can do it in linear time. We saw it. Can we do better? In some cases, can we do better? This is the main question we want to answer, and this leads to what is, say, the query optimization task. Okay. So let's see again. I want to make the end of those three terms: Brutus and Caesar and Calpurnia. So the query is this one: Brutus and Calpurnia and Caesar. So first question. In terms of efficiency, if I do the end of Brutus and Calpurnia and then of Caesar, or whatever else, Calpurnia and Caesar and then Brutus, in terms of effectiveness, is the same. In terms of efficiency, is it the same or not? And why not?
Because you then have to annotate the end, and then so it's just one.
The end, in terms to make it clear, in terms of effectiveness, is exactly the same. The results is correct. Done. Now the question is whether we can do it more efficiently if instead of doing this and this and this, we'll do this. So we put parentheses somewhere. This is the question.
It's better to start with the two shorter list.
Why? Because if I start with a shorter list, the result is a shorter one, and thus I have to compare. Since I remind you that the complexity is x plus y, if instead of y I have something smaller than y, that's better, right? So whenever it's possible, start with the shorter posting list. Does it make sense to everybody? Okay, good. And indeed, this is the strategy, and this is part of the optimization strategy. Okay? So if you want a kind of intuition, again, this is a sentence from the book from the book of the course, so the information retrieval book. And if we start by intersecting the two smallest posting lists, then all intermediate results must be no bigger than the smallest posting list. By definition, is an end, right? So in the best case, you'll take all the elements in the smallest posting list. Okay. And we are therefore likely to do the least amount of the total work. Makes sense. So going back to our example. So basically, you start with Calpurnia and Brutus. And then you'll do Caesar, okay? So basically you have Calpurnia and Brutus. Why? Because are the smallest posting list, and then you do Brutus. Okay. Good. Now, another example. Suppose that you have this madding or crowd and ignoble or strife. Okay? So now we'll consider again something that we didn't consider up to now. If you remind our definition of posting list of the data structure, we have the collection with the terms, the frequency, and then the posting list. So now we can understand why we need the frequency. Okay? So we have parentheses, so we have to do the OR. Okay? Good. So what, but we also remind that we need to start from the smallest sites in principle according to what we saw before, right? So how can we estimate the result of the OR without doing it in order to select whether we do like to do more one or the other or before. The OR in the worst case is the sum of the occurrences of the two terms. The occurrences of the two terms is in the posting list, right? Because we have it in our data structure. So that's why we use the document frequency. It allows us to estimate the size of the OR. And thus to process the query in increasing size, increasing order of OR sizes because of the argument we saw before. These allow us to optimize the query. Okay. So let's make a simple example. We have this query, tangerine or trees, and marmalade or skies, and kaleidoscope or eyes. And those are the frequencies. Okay? So if we want to have a raw estimation of the size of the OR, what can we do? We saw it before. We sum up the frequency of the two terms. Because in the worst case, there are no documents not posting that are in both the posting lists, and thus I have to sum up. This is clearly an upper bound, but it gives us a raw idea. So tangerine and trees is this stuff. Kaleidoscope and eyes seems to be the smallest, right? Roughly. So I will do first this one, then this one, and then this one. Making the hand first of this and this, and then with this. Why? Because here I'm putting together both the observation we made before. Observation A. If I have several hands, let's start from the ones with the smallest posting list. So how can I estimate the posting list here? I have a rough estimation because of the size of the frequencies, right? And so I use this estimation in order to select which part of the queries I have to perform first. Make sense? Good. Okay. Now, before proceeding, okay, now we have seen Boolean queries and the collection of, in this particular case, are documents. Just to be sure that we have a clear picture of what we are doing here, this course is named Web Information Retrieval. So the collection of documents is what? In general, web pages, but I would say whatever you can find of the web in terms of information, okay? So usually are web pages. It could be tweets, posts, and so on and so forth. And you saw yesterday with Luca that there is a clear a significant difference between those documents and the ones we are considering now. Now, just focusing on Shakespeare plays, clearly Shakespeare plays are pretty static in the sense that they've been written by Shakespeare and that's it, done. A web page is a little more dynamic because it can possibly change over time, in particular if you are considering, as an example, pages of news or stuff like that. Social content are extremely dynamic. So one main difference is the dynamicity. Second main difference, here we are considering mostly text, while in general modern web content can be text, video, audio, blah, blah, blah. Third main difference that we will see very clearly further on during the course is that the web is named web. Why? Why the name web? because of links. So, an important question that we have to answer is, if we have a linked structure, namely, the documents in the collection are linked, what happens? And actually, this is the main intuition that has been exploited by Google or modern search engine in order to provide excellent results. We will see. But keep in mind, okay? Anyway, still, web pages, their essence are text. And thus, all those techniques are crucial in order to get relevant information. But don't forget that when we will move towards proper web content, something different will appear, in particular the structure of the web pages, the structure of the web that will help us to provide better results, to improve the quality of the results. Okay? Don't forget it. Okay, now, up to now we have seen Boolean queries. So we saw terms and or not, possibly distance terms or wildcards, stuff like that, but Boolean queries. Now, what is a phrase query and phrase queries? Assume that we want to answer to queries such as Stanford University or University of Rome La Sapienza, where the phrase is we want that everything is there. University of Rome La Sapienza. Okay, so the risk is that if we use university and Rome and La and Sapienza, and La Sapienza probably, because you have a number of false positive, right? Because you can have documents that have all those terms, but not one after the other. Okay, so if we want to answer those kind of queries, the sentence, I went to university at Stanford, is not part of the answers. Because Stanford University does not appear as a phrase in that sentence. Okay. Now, what is interesting is, and this is why we are considering phrase queries, is that as we discussed it before in WestLaw, phrase queries or forms of phrase queries proven to be more effective for answering to the real user to the real information need of the users. And indeed, as you confirmed, in most of the cases, those are the kind of queries that you use when you interact with Google, right? Okay. Clearly, you can have explicit queries, so exactly matching, or implicit queries, something that should contain. Okay. Now, for those kind of queries, it's clear that it's not anymore sufficient to have term docs, term postings. Because again, if you want Stanford University, if you have term docs, this is a perfectly answer to the query, but actually it's not what we want. So we need something more. Okay, what can we do? The first answer we will discuss is very simple. What can we do? What is a term? As a term. Excellent. This is the concept of Biwords. So we have single term, Stanford, single term, university, and then we have something named the Biword, which is Stanford University. And this become a term. Okay? So the idea is that the term is not written on the stone. I don't know whether this is English, actually. It's a raw translation from Italian. Anyway, it's not something that is once forever. The concept of term is up to you. So you can basically insert a new term that is Stanford University. So this is the first attempt, and is named the B word indexes. And what you do is instead of indexing only single terms, you also consider a pair of terms. Okay. So, in this example, in which the text is friends, Romans, and countrymen, you have basically friends, Roman countrymen, and then you have friends Roman as a term, and Romans countrymen as another term. Good. And now all those terms go into the dictionary. Clearly, the main problem here is that with this idea, if instead of Stanford University is La Sapienza University of Rome, you have to add 3 terms, and then 4 terms, and so on and so forth. And what is the problem again? The problem is that the size of the dictionary explodes, okay? Grows really big. Indeed, the main problem you have is that how to deal with longer queries. As an example of queries in which you have, in this example, you have Stanford University Palo Alto. Okay, you can consider Biword, 3 words, 4 words. Done. This is one solution. Or you can try to combine, using the hand, Stanford University and University Palo and Palo Alto. The problem is we have already discussed it before when we thought about the main idea in order to build this solution, and this is prone to false positive. And actually it's very difficult to understand whether you have a false positive or not unless you go and you actually explore the documents collection. So this is to some extent an ineffective solution. Indeed, if we want to summarize all this discussion, we have false positive, and more importantly, the index blew up because you have a very large dictionary. Okay? Indeed, in order to answer, remind me please, what is the problem we are addressing now? Phrase queries. Okay? So we are looking for a solution for phrase queries. The first answer is Bwords. It's not actually the standard solution for those arguments. So let's see what can be a possible solution. Okay, one solution is what is called positional index. So what you do for each term, not only you store the frequency, not only the document, but also the position into the document. Okay? So you come up with something like this. You have the term, the documents, and then for each document you have the position of that term in that document. Okay? That seems to be a pretty reasonable solution. So, as an example, if we consider B in document 993427, if you consider B, the frequency of B is 993427, and in document 1 is in position 7, 18, 33, and so on and so forth. In document 2 is in 3 and 149, in document 4, etc. Okay? So what can we do in order to solve phrase queries? We can use actually a merge algorithm that is pretty similar to the ones we saw before, but we have to iterate both on the document and on the position. It's not sufficient anymore to iterate only on the documents in the posting list. Once we have seen that a document is in both, we have also to iterate in the position in the document in order to answer to the phrase query. Okay? So it's not sufficient to deal only with equality. So this is an example, the classic to be or not to be. So what we can do in order at least to check the to be. Now, to and be are both in document 4. And this is the first iteration of the merge as we saw before. This is 2NB. Now we need 2B. It means that the index of 2 must be one position before the index of B. So among all the possible solutions, only these, because it's 190, 191, 429, 430, and so on and so forth. Okay? The concept is exactly the same we saw before, but now it's not sufficient to see that this term is in both the documents. We also need to consider the position. And this is for 2B or not 2B, etc., and so on and so forth. Okay? Now that we see this technique, it should be clear, at least in principle, how to implement the proximity query we saw before in WestLaw. This /3, which means that these terms is within 3 terms to this term. Okay. Clearly, if you have positional index, you can implement it. Okay. Good.
Can you go back 1 second to the previous slide?
Yeah.
In this case, the numbers refer to positions inside a single document.
In this say syntax, you have documents,
number 2, okay.
position. So 2 appears in document 2, in document 4, in document 7, and in document 4, 2 appears in position 8, 16, 190, and so on and so forth.
Okay.
So in order to see 2B, the first thing is you want documents in which both 2 and B are there, and so you do exactly what we did before. You walk through the lists in order to find those 2 indexes, but it's not sufficient, because then you want that 2 is a position before B in order to have 2B. And thus, among all the possible solutions, only the ones in which you have those arrows are the ones that you have to consider. And clearly you proceed, once you have 2B, you put OR, and you do exactly the same, and so on and so forth. Okay.
Obviously, for longer periods, it becomes really time-consuming. I mean, if we have, like, for example, 4 or 5 words.
It is, but that's the worst we can do, the best we can do.
So this is the actual method used in this kind of.
This is one of the actual methods used. Okay. Okay, now it's clear how can you solve those /3, because if you have positional indexes, clearly you have a distance between the terms, and so you can check whether actually your hands satisfy the properties of the distance between the terms. Okay. Now, the main problem here is, probably you got it, that if you use positional index, you increase the size of the posting storage significantly, substantially. Even if you can compress indexes, we will see later on. Okay, in the next lectures, we will see how to optimize this stuff. Even if we are discussing with Luca to basically see some improvements, but not focus too much on those improvements, because we want to leave space for something more specifically designed for the web information, for the web IR. And as an example, we want to consider, we are thinking about including in the classes recommendation systems and profiling. And networks. And so, you know, if you want to do that, you have to remove something else. But the idea should be clear. You can optimize this stuff. You can compress the indexes. And we will see some ideas in order to compress the indexes. Okay. Anyway, to go back to your question, Indeed, positional indexes are now used in standard systems because they can actually both answer to phrase queries and to proximity queries. So that works pretty well, both explicitly and implicitly. What is explicitly and implicitly? Do you use the, come on. Sorry, what is the name for virgolette in English? The quotation, yes. Do you use, sorry. Do you use the quotation in Google? Most of the time you don't, I do believe. Because actually, in some cases, the quotation have exactly the meaning of exact phrase query. While if you don't use the quotation, is the implicit phrase query. Okay? So the phrase query is part of the results. Okay. Now, just to have a rough idea of what we are talking about, why the size of those positional index increases? Clearly, we know why, because we are adding other information, and but to have a raw estimation of the increase in size of those positional indexes. Clearly, the index size depends on the document size. Usually on the web, we have relatively small documents with less than 1,000 terms. While if you consider books or say other standard documents, you can have up to 10,000 terms. Okay? Good. Now, let's assume that the terms occurs 0.1% in a document. Okay, just to have a rough idea. The idea is that if the document size is 1,000, the positional in postings is 1 because of this 0.1%. But if it is 10,000, is 100. Okay, so you see, it's pretty big. Okay, so clearly this can be a problem, and we need some solution to save space. And again, compression is one of those techniques. In general, just as a rule of thumb, you have a size of positional indexes that is usually 2 to 4 as large as non-positional ones. And in terms of volume, you have an amount of volume that is between 35 and 50% the one of the original text. Now, here there is a caveat. This holds for English-like. Why? Why we are talking about English-like?
Languages that are more concise and have less variation among genders and stuff like that.
Okay, now, don't considering the details, what is important, and you got the point, is that depending on the language, you have different statistics on the occurrences of terms. And thus, those numbers can change dramatically if you consider other languages. Okay? So that's the main consideration. So depending on the language, those figures can change, and you have to take it into consideration. For English-like stuff, you have this kind of bounds. Clearly, you can combine schemes. What do we mean by combine schemes? You can put together Biwords and positional indexes. Why? Why should I do it? What is the typical example of using Biwords? Our name and surname of the so-called VIP or whatever, a relevant person. Okay, here the example is possibly a bit outdated. I don't know whether people is now looking for Michael Jackson or Britney Spears. Anyway, you could have something similar with name and surname. But the idea is that important people name and surname is key for a lot of searches. So why B-words are better than positional indexes?
Because they are unlikely to appear as separated terms.
They are unlikely not only, but because of the efficiency of the query, right? I mean, B-words is a term. So you can easily, as an example, you can use hash function in order to index the terms. And so you can have, in principle, constant time to access the term. Then you have, again, x plus y in order to merge the two terms if you have this posting list. But in order to access the term, it is constant. While, oops. Sorry. While if you use positional indexes, those queries are extremely more complex. Because you have to find Michael, and then you have to find in the same document when Jackson appears, which is not the same as finding Michael Jackson as a term in the dictionary. That's why it can be convenient, the combination of those two techniques. Questions? Okay. Sorry, for today that's it, but we'll see you on Monday and we will go forward.